What? How do you do this? How do you estimate the uncertainty? I mean, what was the first part about? Like, what are you supposed to do with on the first part? Calculate lah, not calculate lah. Huh? Like estimate the area under the graph, right? Wait, sorry, yeah. I mean, I'll open it up as well at the same time. Okay, right? As in, I'll just keep it on the side here like this. Um, estimate. How do you estimate in the first place? Or you move the curve over. So if you move the curve over, wouldn't that be like a? Wouldn't that be like a? Like, isn't that just a straight line here? Would it not be? It is, right? Hey, if you take this portion here and you cut it out and you paste it over here like this, you fill up a triangle, right? Then that's just a triangle lah. Is that not how you did it? Do you why? You're trying to find the area under the graph. Oh, you went to take this curved triangle thing here and you went to jigsaw puzzle it on top here. Is that what you did? Okay. So what she did was she went to take this like triangle here and then she went to put it up there like that. Yeah. Is that what you did? Okay. I mean, is your answer very close to it? Quite close? Okay lah. Then what you asking me can or not? Can lah. Right? Very worrying thing is you need to what do you need to do there? Estimate the uncertainty in your answer and explain your reasoning. Estimate the uncertainty to your answer and explain your reasoning. You know what I'll do? I'll just skip this question. Yeah, just keep it lah, right? Okay. So hey guys, one thing especially those who are going MYE like mid-year exam tomorrow and then mid-year exam next Tuesday, right? Okay. Listen the NJC students just did the exam the MCQ, right? First three questions were killer questions. First three MCQ. They made you calculate. Go and ask Roshni, right? Calculate. I opened the paper, right? I looked at it and I was like thinking, I will just skip the first three questions. No, she brought it to me the other day and she showed me. No, MCQ, you can bring the paper home. Yeah. So I opened, so here's the thing, I literally opened, right? The first thing on my mind, I was like looking at the first three questions, I will skip these three. Like if you give me 30 questions and if I didn't know how to do, like let's say like it's not even blocked anyway. So if I had to give up some questions, I would just give up the first three. Like literally, like I okay, but here's the thing, you should be aware of this, right? Teachers intentionally put the very difficult questions at the front, right? And they like to make like seemingly easy questions like kinematics and dynamics, they like to make it very difficult. It's a shock and awe effect. It's like, oh, I made you waste all the time in the first three questions. And then by the time you flip to the last few questions, you realize that hey, actually all the other questions can do one. Which is what happened when I kept on flipping the questions. I realized that all the questions at the back were easy. So she wasted a lot of time on the front question trying to calculate some what like this there's this projectile motion, this object is moving this way and then the object is moving this way. It's not okay. At some point, right? At some point, you all have to understand this. It's not about trying to get all the marks. It's about trying to get what you can and then come back to the other stuff, right? Don't be so focused on getting everything correct or getting everything right that you completely mess up your time management. Time management is super important. Okay, right? It's not that you don't know how to do, no, you know how to do. If given enough time, you will definitely know how to do one. You just have to go and work this out, work that out, and then arrange this equation here, arrange this equation there. But you ain't got time, right? Don't waste your time on those things. Go and spend it on other things. Okay, time management is super important. I don't care what other, like what you feel about it, right? But time management is super important. Okay, um I said I want to skip, right? I will skip this question, right? But I mean, I'm trying to figure out the answers like myself, lah, right? Estimate the uncertainty in your answer to A part one. How would you estimate that? Uh, Huh? I mean, I would lah. Oh, there's answer at the back. Okay, wait, wait, wait. No, that's the explanation. Explain why do you like have this amount of estimation. The question is how do you how do I come up with a value for it? You know what? If anything, right? I'll give you a 5% rule. Like if you ask me to do this kind of thing, this kind of question, I will just assume that I will be close to 5% to the correct answer. So I'll just take 5% of the value that I got here. Yeah. I can't go any okay, to me, right, I don't think I should do 10% error. Right? A 10% error is a little bit too big. That means like I know I have an inability to count squares. Right? I would say 5% is a good number. So 5% of how much? What's the total distance? So it's 2,600 as the total distance. So 2,600 times 5% is how much? Was that? Oh, is that the reason why it's 130? Yeah, I think it's probably the reason why. 26, 2580 to 2700. But that's not the uncertainty, that's the range of answers. So the uncertainty will be what? Like yeah, I know, but how did they come up with their values? I don't know idea. Yeah. Yeah, you can I think we probably just ask the school like what's the rationale behind it. For me, I'll just go with a 5% rule. It's kind of like this. If you ask me to estimate something, and if let's say you ask me what's a good percentage for estimated uncertainty, right? I would say 5% because if I hit 10%, that means I'm very bad at yeah, that would be indicated as a very very bad way of estimating really if it's 10%. It's like your practical, right? If you have a 10% error, that's considered not so good, right? Right, so it's be less than 10, right? So I'll go with 5. I'll just take 5%. Like yeah, but I'm not too sure what they actually do want. If you want me to think of a more convoluted way of finding the uncertainty, this is what I'll do. I would take the largest possible error triangle and the smallest possible, right, triangle like this, and I'll use that as the max minus min divided by 2. Yeah, I would just take it as the largest possible um triangle and the smallest possible triangle as my error here, like this. Like that, I will just do that, and then I'll just find the difference between the two areas. Yeah, and then I'll just say max minus min divided by 2. I'll say that that's my estimated uncertainty. Yeah, yeah. You know why? Because like what Pez was saying, Pez, what did you do? You went to draw a line straight through the middle, right? You went to draw a straight line straight through the middle. So I'll just take a line that is steeper and a line that's like less steep. Yeah. Okay, yeah. There we go. That was a bit weird. Okay, next one, come. Yeah, yeah. This is a famous RI question. Yeah, RI created this question. This was back in like 2018 or something like that. 2017, 2018, I guess. And then after that, like schools just recycled this question many times over. Actually, I don't know. I think RI's one was the other way around. Like someone hit the golf ball up, and then everyone just started doing downwards. I don't know. Yeah, random one. Because you're not supposed to copy RI questions. Yeah, I remember now. Because if you copy RI questions, RI will come here, like come to you with a lawsuit. Yeah, they are really annoying. Yeah. So I don't have RI notes, okay, guys. I also don't have RI papers, huh? I mean, for the record. Okay, anyway, yeah, come. What's the next one? Oh, so you're talking about this. Oh, okay. So the to solve this question, I mean, like because I've done this a couple of times already, so like to me, no. I mean, it's like I just tell you what my logic is lah. So my logic is this, right? I just ignore the slope. I just imagine that he's hitting a ball off the side of a cliff, right, at an angle of 14 degrees to the horizontal, and then it lands. So by the time it lands, right, I go and find this angle here. Like I go and find the horizontal component and the vertical component, right? Horizontal component and the vertical component like this, right? Okay. And then what am I supposed to do? I'm supposed to. Oh yeah. You find the vertical displacement, you find the horizontal displacement, and then you find. Oh yeah. Sorry. Oh, that means the RI question is a bit different. Sorry. So that means yeah. So the angle there is the trigo between the horizontal and the vertical. Yeah, he's right. Yeah. Oh, so the RI question is different. The RI question was asking about like what's the angle to the horizontal units. Yeah. Mm-hmm. Huh? No, yeah, that's you breaking it up, right? Yeah. So the thing is that that's not wrong. I'm not going to tell you that it's wrong, but sometimes it will hurt you your other ways that you might do other questions by. Yeah. Like I mean I guess for example like what is the vertical distance? What's the vertical displacement then? Yeah. Right. So y equals to ut plus half at square, right? Okay. Um and basically if you just sub in the total time like from the start to the end, right? And then you have the initial velocity with the initial velocity will be the vertical component upwards, but then the acceleration is negative 9.81, right? Then you sub it all in, then you actually will get a negative y value. Yeah, and the negative y value will indicate a negative displacement. Yeah. Huh? Really? Oh, okay. Yeah, so that's what I'm trying to say. Like some students will try to break this down and then break it down to this point, then break it down to the last point there. So don't do that because I think what happened was in Sec 4, some teachers in the Sec 4 A math, when they're teaching kinematics, they actually made the students break it down into parts. Which is why it's stuck on. The idea of breaking it down into parts stuck on. Yeah. So whenever I teach projectile motion, I always tell students don't break it apart. Just do one whole motion down. Correct. But you see, right, the formula only works for the vertical direction. The horizontal is just speed equals the distance over time. There's no acceleration mark. Mm. So what happens is this u, right? The next common mistake is a lot of students they'll do is they'll go and sub in the initial u as the u here, which is wrong. They have to sub in the vertical component as a u. So it will be u sine 14. Right, this will be u sine 14. And there, you got an angle ready now? Yeah. Okay. Oh, the next part, someone got someone part. The what? Oh, resistance. This one? Huh? Oh, they say there's air resistance and they want you to draw the path, is it? Oh, that's not a good picture. Wait, oh, yo, I can't draw an elephant's head. Yeah, something like that, lah, right? Bad drawing, but okay. Okay. Um, can I do away with this? Can I draw something else for you? Yeah, can okay, good. So I want you to imagine, that we are doing projectile motion off a cliff. Okay, doing projectile motion off a cliff like this, off a cliff, like that, no air resistance, it will land like this. Correct, right? So there'll be an angle of impact here like this. So that will be the angle of impact here. This is the angle of impact. But if let's say there's air resistance, so what will happen to the path? You understand? Right, something like that, right? What if there's a lot of air resistance? Let's say there's a lot of air resistance. Like, how would the path end up looking like? Let's say there's a lot of air resistance, right? The vertical component is reduced to zero. There's no more, sorry, the horizontal component is reduced to zero. There's no more horizontal component. Okay? You're only left with the vertical only. So then what will be the angle of impact, which is steeper than this one? This is like almost 90 degrees. Yes, yes. So air resistance affects both horizontal and vertical. So when you have the presence of air resistance, right? I think what most students forget is that no, what happens to your horizontal? Your horizontal starts to decelerate. Okay, hang on, wait, you all never do? But you got. But never mind, they never do. Huh? Oh, you didn't do air resistance with me before, man? Oh, you only later only, Oh, okay, can. Okay, let's do vanilla, right? Projectile motion. This is your typical projectile motion. Okay. Then let's say I have a projectile motion where drag is significant. So to give you an example of how drag is significant, right? Is I take a piece of tissue and I throw it like this. Right? Do you see that? Right. And the reason why drag is significant to this piece of tissue is because the tissue paper is light. Okay. If I throw it with a ball, sorry, if I throw it with a ball, the air resistance on the ball is like I can't tell, right? But for a piece of tissue, right, like this, yeah, and I roll it to a ball like this, okay, I throw it like this, okay. If air resistance is significant enough and it's falling enough, it actually will eventually fall in a vertical line. Okay, so let me try to replicate that scenario, right? So something with air resistance might look like this. I'm not too happy with this. Hang on. Okay, good. So this is something with air resistance. Now, what's the requirement for drawing a projectile motion with air resistance? Number one, it must be lower. Number two, the range must be shorter. Number three, it must be asymmetrical. Did you hear that before? Okay, now you know. Asymmetrical meaning that it cannot look like a nice parabolic curve, which also means that I have had some there have been some people who have done this before. They have drawn something like that. Air resistance, right? They draw it like that. Okay, if your teacher's stringent, right, 0 marks. Yeah. So this is wrong. Do you know why this is wrong? Yeah, but why does it have to be asymmetrical? Yeah, the horizontal is affected. So let me draw for you a little bit step by step. Okay. The original projectile motion, no air resistance. How does the two components look like? So we start drawing. I'm going to use blue first. Okay, do you understand what I'm doing here, guys? Do you see this thing that I'm doing here? Let me just show it to you. What's constant? The horizontal is constant. That's right. Okay. So in the presence of no, in the absence of air resistance, the horizontal velocity is the same throughout. But the vertical velocity, as in like it will start decreasing. In fact, it will be zero at the top. Then it will start increase again as it falls. No, the word terminal velocity can only be applied when there's air resistance. So if your projectile motion has no drag, you cannot mention terminal velocity. Yeah, you can only mention final velocity. So a projectile motion with no air resistance is perfectly symmetrical, right? Which also means that the final velocity here would be the exact same angle and exact same speed as the start over there. Okay. But if air resistance is significant, like in the case of the red color path, then your air resistance, sorry, your horizontal will be affected. In fact, the horizontal will, what I do is this, I put it up there, but then I shorten it a bit. Then I put it up there. Ooh, shoes. Then I shorten it a bit more, like this. Yeah, like this, right? Then the horizontal keeps shortening, right, like this, right, like this. You see that? Right, it gets shorter and shorter and shorter, and eventually, what happens to it? Yeah, it almost becomes zero. You can even say that it becomes zero if you want, I suppose. Right, I can't even make it any shorter anymore. Wait, hold on. Yeah, there we go. Something like that. Okay. And then eventually it basically goes away, like it disappears. The horizontal component disappears like this. Right. There you go. Right. So yeah. So yeah. The red one is air resistance is drag is air resistance. Yeah. Well, sorry, what was the question? What were you asking? Yes, definitely. Yeah, definitely. Yes. Okay. Um, okay, how about the horizontal though? How does horizontal? So the horizontal is a little bit more tricky because here's the thing. As the object is going up, the air resistance on the vertical is acting downwards. But once on the other end, right, on the other end, as the object is falling down, right, the air resistance is acting upwards. So, but then I'm here to draw the velocity. What? Yeah, I'm here to draw the velocity. Now, I'll help you out in a while. Just bear with me for a while. So I'll help you out in a while. So the idea here is something like this, right? So it basically reduces very quickly, right? The you know yeah, the vertical reduces to zero very quickly, right? The horizontal is, yeah, getting less as well. And then yet when it's falling, it increases very slowly. Yeah, that's pretty much it. Okay, so then you can mention that if you look at this, right, you can mention that for the object that's experiencing drag, this is almost or maybe already terminal velocity. Yeah. Well, I mean, what does it mean to be terminal velocity? 什么意思 terminal velocity means what? Fr is equals to air resistance. Whoa, whoa, whoa. Yeah, your terminology is all over the place. Right? So terminal velocity resultant is zero. So what are you saying resultant is more than something? Or you said equals, yeah, resultant equals to zero. Yeah, so it cannot be equal to air resistance, right? Okay, so you're talking about the weight. The downwards weight is a force is equals to the air resistance upwards. Okay, right? So it's likely that towards the end here, this could be considered as terminal velocity, but you must strictly understand that terminal velocity means what? Terminal velocity means maximum velocity, right? Maximum velocity in air resistance, acceleration is zero. That means it doesn't change velocity anymore already. But you see, right, towards the end here, do you still see the horizontal still decreasing? Right? So maybe it's close to terminal velocity, but if it's still decreasing there, we cannot call it terminal velocity. So the best idea to kind of like understand when does it reach terminal velocity is to let it continue falling, right? And if it falls in a vertical line after this, if it falls in a vertical line like that, right, then yeah, that is very likely to be terminal velocity. Like absolutely, there's no more horizontal already. You know what I'm saying, right? So yes, right. So on the going up part, air resistance acts downwards and backwards. Yeah, right. At any point, let's say I give you like say air resistance is drag. Okay, drag is green. Okay, for example, drag. Right, drag is green. Let's say I ask you, okay, at this point here, right, where is drag acting? What's the direction of drag? Is a tangent to the curve pointing backwards. Right, it's a tangent to the curve like this, pointing backwards like that. But then that means that there's two components. What's the two components? Backwards and downwards, correct? Right, backwards and downwards. So be very careful. My arrows are not well labeled, right? Be very careful, right? Like the orange one represents what? What does the orange arrows represent? You're not colorblind, anyone? No, right? Okay. What do the orange arrows represent? Like when I was drawing the time, the orange represents the velocity, yeah, the v, right? The speed here. This green arrow that I'm drawing here represents the drag, which is air resistance, which is a force, right? Which is a force. So be very careful because I always make it a point that students, should not confuse between force and velocity, right? So yeah. Okay. So this backwards, like if I split the air resistance into two components, backwards and downwards, the backwards causes the horizontal velocity to get lesser and lesser and lesser. Okay. Whereas the downwards will cause the vertical velocity to become lesser, right? But hang on, the original projectile motion, the one without air resistance, is it not already getting lesser and lesser and lesser? Like what was it getting lesser due to? It was due to gravity, right? So you got to understand that when you have air resistance, the vertical velocity is reduced, is getting lesser because of gravity and air resistance downwards. So like it's like both air resistance and gravity acting on the object downwards. So therefore his vertical velocity becomes very small or becomes zero very quickly. Right? This guy, the vertical velocity only becomes zero here. But then this guy, the vertical velocity becomes zero here, like just before it, like this, right? Earlier. Okay? And then yet when you're falling down, the time when you're falling down, the air resistance acting in which direction? Let's say I give you a point here like this. Where does the air resistance act here? It's acting at a tangent upwards like this, right? Air resistance is acting like this. Right, sorry, I need to draw a tangent. Right, this will be the drag, like this. Which means that there is what? There is a upwards component and a leftwards component. Downwards like this? No. So air resistance acts against motion. So if your object, right, if your tissue paper is falling this way, wait, look here, falling this way, then the velocity, so the red color is the path, right? So it points this way, then the air resistance will point opposite of its direction. Cannot. Ah. The what downwards? What are you talking about? Which one? This one is it? Okay. So you're saying that isn't the velocity increasing? Correct? Yes, it's increasing, but it's not increasing at 9.81. Yeah, hang on. So you see, right? The vertical velocity here, the acceleration downwards is 9.81 meters per second squared. Correct? Okay. But for the downwards motion of drag, right? When drag is not negligible, okay, the downwards velocity is increasing, but it's increasing lesser than 9.1. Okay. Okay. Hang on. Let me help you out here. So are you focused about these three arrows here? Are you talking about these three arrows here, the downwards arrows here? Huh? Are you, yeah. So what happens is the arrows are increasing because of gravity, right? But air resistance is acting against gravity, right? Acting against gravitational force. So the rate of increase is not as great as that. Hang on, wait, hang on. Let me put this to the side because there's actually a very multi-layered understanding for drag. Okay, multi-layered understanding for drag. Let me drop a ball. Let me drop a ball in the presence of drag. There's drag. Okay, let me drop a ball in the presence of drag. Okay, right. At the very start, how much drag is there? At the very start, when the u is equal to 0, how much drag is there at the very start? 0. No drag, right? Okay. What's the only force that's acting on this ball? And therefore, what's the acceleration of that ball? So at the very start, the downwards is acceleration is 9.81, right, meters per second squared. Correct. But just a while later, as the object falls, okay, the weight still acts on it. It's the same weight. It's the same weight. This is the same weight as this. But then now you get what? You get upwards drag. Correct? So there's upwards drag now. Okay. So what happens to the acceleration there? Right? The acceleration is now less than 9.81. So if I ask you to draw a velocity time graph, right? Let's say I ask you to draw a velocity time graph. Okay. Let's say I ask you to draw this velocity time graph. Like how does the velocity increase from 0? Like this. Let's say I ask you to draw all the vertical velocities, right? Time graph there. Like this. How would correct. You will see this. Right? You will see decreasing acceleration, right? What does decreasing acceleration mean? Caught you there. Decreasing acceleration is not deceleration. Decreasing acceleration means that it's still accelerating, but the acceleration is getting less. Right? The acceleration is getting less. Okay, it's kind of like imagine like every month you earn some money, but every month from now you earn let's say you start off with 1,000, but then your boss say that every month from now I will have to pay you less. Next month I'll pay you 900. Next month I'll pay you 800. Okay, so the idea here is then you save all this money. For example, right? This month you earn 1,000. Next month you earn 900. Next month you earn 800. But is the bank account still increasing? It's still increasing, right? But the amount of increase each month is getting less. So what we have here is called decreasing acceleration. Okay? So that's what's happening here. This one. The vertical portion here is decreasing acceleration. Can? Mm. You can say that. Okay? You can say that. But you know where the confusion is? So over the years, I've seen a lot of the Sec 4 students, they come to me and then they ask me why is this not deceleration? Because in school, right, they hear the teacher say this, the teacher like to say this. The velocity is increasing at a slower rate. This is why it kind of like clicks in their head and they're like, oh, it's slower, right? Then that's where the problem starts. So that's why I don't like to say, right, that like just yes, you can say that the velocity is increasing at a decreasing rate. But yeah, okay, can I? Whereas if there's no air resistance, then the vertical velocity will increase at a constant rate. It will increase at 9.1. If I were to overlay the vertical velocity here on the graph, it will look like this. It will have the same initial gradient because the same initial gradient is 9.1, but then it will maintain the initial gradient. So this one here is no drag. Okay, very quickly, right? Okay, I don't know whether you notice this, but I like to split, right? Analyzing the vertical and horizontal separately. I don't like to combine it into the diagonal, right? The diagonal makes no sense to me. It's very hard to understand. So that's why I like to split it into horizontal and vertical. So you see the horizontal, right? Horizontal velocity is decreasing, right? You can draw, if let's say they ask you to draw the graph for the horizontal, right? You just draw the horizontal decreasing at a decreasing rate. So V horizontal, this is the horizontal V, which is this one here. Okay, this one here like this. And I ask you to draw a graph of the V horizontal. You know that it's going to decrease. In fact, it might even decrease down to zero, right? But the graph will be drawn like that. Yes. Yeah, V horizontal. The horizontal velocity for the one that has drag. Decreasing at a decreasing rate. Why? You wanna ask? I mean, it is decelerating, lah, right? Because it's getting to zero, right? Right? It's, the horizontal speed is decelerating. Anybody wants to ask me? Why is it not a straight line? Why can't we draw it like that? Or why can't it be drawn like this? Right? Okay. Okay, Ken. What? What? Yes, you got it. What? Huh? Fast what? I mean, this is a horizontal speed. I'm trying to draw the graph of this projectile that's experiencing air resistance. I'm trying to draw the graph for its horizontal speed. So you can see the horizontal speed decreasing, right? Okay, it's getting less and less and less. In fact, it becomes zero towards the end, right? Okay, so then I tell you that the graph of the horizontal looks like this. Then I challenge you and ask you, why is it not a straight line? Right? Or worse, why not? Why is it not like that? But here's the thing, graphs, right? Graphs, guys, look graphs, there's only three general shapes. These are the three general shapes. It's either decreasing at a decreasing rate, decreasing at a constant rate, or decreasing at an increasing rate. Okay? Yes. The deceleration. Of what? Horizontal or vertical? Okay. No. It's decelerating at a decreasing rate. Yes. Yes. Become gentler. There you go. There you go. Yes. Right. So that's your question. But my question is, why is it decreasing at a decreasing rate? Why is it not a straight line? Why is it not decreasing at an increasing rate? Yeah. So why is it not constant rate? Okay. Drag. Yes. Wow, well, I'm gonna throw something at you. Wow, you were doing so well, then suddenly you just jumped off the cliff. It's got nothing to do with Newton's third law here, dude. Drag is proportional to speed. Okay? So the idea here is, yes, you experience drag at the start horizontally, right? And therefore the horizontal speed of the projectile gets less and less and less and less and less. All right? But because of that, the drag amount gets actually less and less and less and less. So the resistive force gets less and less and less. The deceleration gets less and less and less. And therefore, the graph must look like this, right? Yeah, deceleration is getting less. So the horizontal velocity is decreasing at a decreasing rate. But this is the important part, right? Drag is proportional to speed. Yeah. Oh, sorry. Recently, like in the last couple of minutes, I feel there's a. Hmm. Maybe I should sleep more. Yeah, I don't know. Maybe I need more. Okay, can I? Everyone okay with this? Okay. So there's also another very popular question they like to ask, right? They like to ask this other question as well with regards to up and downs. Okay, it'll be something like that. So let's say you throw a stone up, right, and it falls back down. Then they ask you draw a graph for this. How do you draw a graph for this stone? Velocity time graph. Correct. Correct or not? Right. No air resistance. No drag. No drag. Right. Then it'll look like that. Right. Okay. What happens if you throw a piece of tissue up and down? So what I'm showing you here is pretty much like projectile motion, but I'm not showing you the forward motion. I'm just showing you the up and down motions. You get what I'm saying? Like if I throw something up and down, okay, I'm just showing you the vertical part of this. I'm showing you the vertical part of this projectile motion with drag. Sit down. Hey, but actually you had a test today, right? How was it? Oh, okay lah. Then just minus 3, okay? So 47.50, ah. Okay, so I'm just gonna show you this. Okay, so what happens if you do throw, like let's say a piece of tissue, you throw it up like that, right? What would the path look like? If it's just vertical only, wheel. That's it, right? Right? It just wouldn't go as high, right? A demo, okay, that's not a good demo. That one it just actually touched the ceiling, right? Okay, something like that. Right? You get what I'm saying? Right? So you got that right? Like this one more time. One more time. Okay, fine. Right. I'm done showing tissue paper. Can I draw the graph for the tissue paper? This is the vertical. Okay, it will look like this, it will curve like that. Okay, it will curve downwards because we said decreasing deceleration, right? Sorry, okay, so the graph for the tissue paper will look like this. Okay, if this comes out in your papers, right, it's a 3-mark graph drawing. This thing here is 3 marks. Is that okay? It's not. No, I thought it's a mosquito. Yeah, I know, right? Okay. Number one, decreasing deceleration. Number two, right, it tapers off to a almost terminal velocity. Number three, that's not a mosquito, right? Okay, just leave it alone. Number three, please pay attention here. The point where it crosses the x-axis, these two gradients must be the same. Why? So it's very weird, right? Like I draw this graph, right? How come this point here and this point here must have the same gradient? Okay, it's because these are the tops of their trajectories, right? What's the speed at the tops? 0 and 0, right? Both 0, right? What's the only force acting on them at that point? Gravitational force, mg, right? So therefore, what's the acceleration at that very point? 9.1. So both of them will have the same gradient. The black line is 9.1 throughout. The red one is only 9.1 at the very top of its trajectory, because everywhere else there's that problem with air resistance. You understand that? Okay. So there's this time that's okay. So next concept. There's a time of it going up, and then there's a time of it going down. Right? I want you to compare the times. Compare the time. T up versus T down. This is T up, and this will be T down. T up is lesser than T down. Right? It's a moth, like it's a tiny little moth. Leave it alone. Leave it alone. Let it fly. I'll just strip it away later. What? Yeah. Why? Why is plus? Right? Uh, uh, uh. So T up is because mg plus air resistance pointing down. T down is mg pointing up, air resistance pointing, sorry, mg pointing down, air resistance pointing up. So, I mean, I'll draw it out for you. So as it's going up, the mg is pointing down, the drag is pointing down. So what's the deceleration like for an object that's experiencing air resistance as it's going up? What's the deceleration like? Like the total deceleration is more than 9.1. That's why your first initial line here is steeper than 9.1. Right? So the acceleration is more than 9.81 meters per second squared. Okay? But then when the object is falling down, as is, I draw the V pointing downwards here like this. Okay? The mg is pointing, down, and the drag is pointing up. Okay, the drag is pointing up, and therefore the acceleration downwards is less than 9.1. Less than 9.1. Okay? So what this means, right? What this means is that when you are experiencing air resistance, for the same height that you travel, it will take you faster to get to the maximum height, but then when you start falling, it will take you slower to get back to the original position. Right? Fast to slow down, slow to come back down. Yeah. Okay, sorry, I need to go through your questions. If not, you all will be like so frustrated. Okay, let me go through your questions. Okay, can right. So this is a crash course on objects with air resistance and the graph and the concept. Okay, and you have to be very careful with the resultant force word that you use. Right. So you have to kind of like train yourself a bit for it. Okay. So sorry. What's the next one, Anthea? Eugene, you're not so urgent because yours is next Tuesday, but I kind of like that. Hers is tomorrow, so that's why I have to settle her first. What's that? 3B. Where's 3B? I don't see 3B around. 3B. 3B, this one? A proton is at rest at point P when x is equal to 5. Estimate the speed of proton at x equals to 3.3. I don't get this. I don't understand this as well. So you got sphere A and sphere B. Okay? Sphere A and sphere B. They tell you that there's a movable point, okay, that lies along this line, a distance of x from A, surface of A, right? Variation of x of the E field. This is E field, by the way, E field, okay, at point P is shown, E field at point P. So what I see is that the E field, and there the E field changes from positive to negative. So to me, it feels like both of them have the same charge. Both of them have the same charge, such that if you are near this charge, it's pointing to the right. Okay, it's pointing to the right. Then as you go closer to the other charge, then because of the proximity to this charge, and it's a plus charge, so it points outwards, the E field strength, right? Now most of it will point the other way, right? Which is why it goes negative. So that's how I tell it's the same charge. But whether or not, but you know, it might be minus and minus, I don't know. Yeah, I don't know whether is it minus and minus. Okay. So then they have this weird ass question where they say the proton is at rest at point P when x equals to 5, and they say estimate the speed of the proton at x equals to 3.3. Okay. All right. So where's 5 and where's 3.3? Okay. 5 is here and 3.3 happens to be at that point there. It's such a weird question. Right. So you put a proton here like this, right? Okay. Oh my god. Okay. Yeah. Wow. This is too much lah. This one. These teachers are really too much. Why your teacher like that? Okay lah. At least they're not ASR type of questions. You know what I mean? But okay. So firstly, right? You know what's the big problem? The big problem is it's either plus plus or minus minus. In fact, I don't even know yet. You know what I'm saying? Right? Okay. Secondly, okay. So you know what? Let's just assume it's plus plus first. We work out the minus minus later. Okay. When the proton is here, what's the speed again? What's it? Huh? Is at rest, huh? It's zero, right? It's at rest, huh? So it's what they're saying is that I take a proton and put it here. Okay? Then I let go of it. Where would it go? Where would it go? It will definitely go this way, right? Okay, it will go this way. So if it goes this way, the question is asking you, so what is his speed here? He's asking you what's the speed, right? What's the speed at the 3.3 speed of proton here, like this. Okay? So because the proton is being, is moving towards this direction here. However, do you notice the question is saying, what's the question saying? You know what the question is saying? The question is asking you to estimate the speed. Estimate again area under the graph. Hey, hello, enough of this area under the graph nonsense, man. You need this area. Okay? Alright. What does the area represent? Under the E field strength graph, the area represents what? Nope. Almost correct, but not right. Area under E field strength graph. Ah, this. You were almost correct. You were almost correct, but it's not energy. Yes, it's potential. Yes, potential. So the area is potential, right? In fact, the area is the change in potential. So what you're supposed to do is supposed to estimate the change in potential with this area. Okay? Wow, annoying eh. Someone in CM, you have to change it to meters eh. Right? Then you find the area here like this. Yeah. Okay? Then you multiply it to the charge. So the change in KE will be equals to the charge of the proton times the change in the potential. The loss in EPE is converted into KE. Then you go and find the V. Your head lah. Like physics charge lah. Chemistry charge is 1. Physics is 1.6 times 10 to the power minus 19 coulombs. Oh yo. Hey Amanda, fun or not? You hear me teach them? Fun or not? This is what happens when you go to J2. Okay? No I'm so scared for you all. What the hell? Yeah, so 1 point. That one is in your formula sheet. Yeah, but you have to pull it out lah. Okay. Right. So annoying this question. Okay. Hey, but you know why this question is even lagi more annoying to me or not? They never say that it was positive, leh. Huh? No, no. As in like they didn't say that it was positive. What happens if it's negative? Huh? What happens if it's negative? So the answer is it's not possible. It's not possible for the question that they ask for these two sides to be negative. You know why? Correct. The proton, if you put it here, it wouldn't move here. It will move there. If both sides were negative, if let's say this side here is negative and this side here is negative, and you place it here, right? It will be attracted by the negative charge. It wouldn't move to the 3.3 mark. Then it wouldn't make sense to ask a question of like what's the speed when it's here. Proton what charge? Positive, right? That one negative, right? This one boy, that one girl. Then of course boy attracted girl lah. Like the boy wouldn't come to here. What? ah, no, but here's the thing, right? The charge they say they place it on the 5 cm mark, right? It's actually not at the null point. Or it's not on this side. If it's on this side, it will be attracted over there. But because it's on this side of the null point, right? That means the field from this side is stronger. So if you place a proton here, it will not even go over that side. It will go over here. Because the question says you place a proton at with an initial speed of 0, right? They place it there with a speed of 0. Okay? So which means that if you let go of it, this proton wouldn't go there, it will go here only. So there's no way for this proton to go towards the 3.3. Yes? You understand now? In fact, I think there's a question there, you know. Is there a question later on they ask you, so what's the charge of P and Q? Did they ask you the charge of no A and B? Huh? I, where? Or they just went to something else? Chey. Yeah. So I mean, I'm just telling you that you have to be able to tell that these two charges, these two spheres are positive charge. Now, however, it could be a case whereby during the exam they make an announcement and they tell the students that hey, for this question, right, we just wanted to add on one thing: A and B are positively charged. Maybe, but I was just trying to show you here that they didn't need to do that. Okay, they didn't need to do that, right? Worst case is that you have to figure out that both of them are same charge and positive. Yeah. That one is potential graph. This one is E field strength graph. Yes, correct. Yeah, correct. So it's either positive to positive, potential, right? Potential is what? Potential is just voltage, right? So positive voltage to positive voltage or negative voltage to negative voltage. That is. Okay. Do you need me to do this one? I don't even know what you're supposed to draw. Oh, what happens when the upper plate is moved further away? Is it? If it's moved further away, what happens to the E field strength? Becomes weaker. So what happens to the electric force? Becomes smaller. So what happens to the acceleration? It becomes less, right? So you're drawing projectile motion with a lesser acceleration, right? Wait, let me think about this first. On Earth, you play golf. Sorry, on Earth, you play golf, the thing will go like that, right? But if let's say you play golf on the moon with the same speed, what will happen to the golf ball? Yeah, the golf ball will fly even further higher up, right? It will just go like whew, like that, right? I think that's the case here. So your path will go something like that. Um, lesser acceleration. So your path will go something like this. Yeah. Yes, you're right. Yeah. In fact, I don't know how many marks is this. Cha che lah. Okay. If I were to draw this very accurately and there, like I would draw a straight line after it exits the plate somehow. Like if you give me 2 marks, I'll pay attention to that. But yeah, like weaker acceleration, weaker gravity, right? You hit the golf ball, pop, the golf ball will fly further higher, right? So it's the same idea here. You separate the plates, electric force is less, pop, right? Then you'll fly further away. Yeah, got sound effect also. Ah. Mm-hmm. How come it doesn't what? Doesn't go out this hole? Because the okay, what makes it turn? Okay? No, when the vertical velocity is zero. Correct, right? Since like and what happens to the vertical velocity as it's going up? It takes a longer time. Yeah, correct. So, but then the horizontal velocity doesn't change, right? So it continues to travel very far away. So it never goes back to the original hole. Yeah. Sorry, I just think of the Earth and the Moon playing golf. Right. I don't actually play golf. I actually hate golf a lot. Like just for the record, in case you think that I'm some golf lover, no, I seriously absolutely hate golf. Right? So, no, it's a very big waste of space. Yeah, I mean you can make a park, right, or something like that for more people to enjoy. What? I mean, yes, it is, right? It is true, right? The Keppel one is gone and all that. The only thing I enjoyed about these golf courses were their little clubhouses where it's open to the public, the restaurants you can go, right? Yeah, I loved it. But other than from that, no. Mm. But they can't take down SICC. Question 5A part 2. 5A part, what the pong is this? What's this? 5A part 1 and 5A part 2. Oh, what's going on here? Sensing coil wound around an iron ring. Hey, wait, what time supposed to be our lesson? Oh, whoops, okay. So I still got more time. Sorry, what? What's going on here? So are you saying that, so according to what I'm looking at here, why do people come up with this kind of weird devices? So what we're looking at here is that this circuit breaker, when it's activated, it actually will pull this section of the wire away, like chop. Yeah, yeah. You know what I'm saying? Like you know what he's saying? He's saying that when it's activated, it kind of like pulls it away, right? So it kind of like looks like this, like the the thing is retracted like that. Let me just draw it out for you. Yeah, like that. It's like nope, right? Then then it gets like it like takes a part of your bone away or something like that. I don't know, man. And then the current is gone. Creates this kind of nonsense. Okay, and the guy, the worst thing is that okay, so what must it what okay, so we work backwards, we reverse engineer here. So if this is how it works, right? If this thing is being pulled inwards, it's being pulled inwards because this becomes an electromagnet, right? And if it becomes an electromagnet, it attracts a stick, right? It pulls the stick in like this, and with that, it pulls a section of the wire along with it, like prap, right? Break, right? So that means it was activated from some electrical device, and whatever it is, the electrical device is connected to a what they call it a sensing coil. So the sensing coil is a coil of wire around the wires. So I guess the idea here is, and what's a circuit breaker used to do? For what? When does it break circuit? When the what? One more time. When the current is too high or when there are too many patients going into the hospital, they will have to call for a circuit breaker. Isn't that what happened in 2020? Okay, anyway, so when the current is too high, current, right, is too high, okay, current is too high, the circuit breaker should activate. So the idea, so what we're trying to do is we're trying to establish that, oh, let's say the current here surges, right? There's a surge in current, right? There's a surge in current. So which means that, what's the coil trying to sense anyway? So it's trying to sense the magnetic field of the wires, is it? So we have to understand that the magnetic field of the wire, like there's this wire has a magnetic field. So the sensing coil is to sense its magnetic field, and when the field is too strong, or when there's a very big change, the sensing coil will send, right? I mean, this is induced EMF, right? This EMI, this EMI in this coil, and then the electrical device will be like, oh, there's so much induced voltage now, right? Let me send the thing to the circuit breaker. Then the circuit breaker becomes electromagnetized, and then it pulls away that section away. Then it cuts off the current. Yeah, you get what I'm saying? I mean, yeah, I mean, isn't that what you were saying? Oh yeah, I also would think that actually, why don't they just connect it directly, right? Why do you need an electrical device? I have actually no idea what the electrical device is. Did they ask? Did they ask, like, suggest what the electrical device could be? Huh? Oh no, no, yeah, fictitious thing, right? Yeah. What's the purpose of the iron ring? What's the purpose of the onion ring to go with your Burger King burger? Sorry, I'm very hungry now, lah. Huh? What? Yeah, concentrates magnetic field lines, and therefore it amplifies the magnetic field of the wire, right? Of the two wires, right? Okay. Faraday's law to explain why the circuit breaker is triggered when a fault in an appliance causes the electrocutor to what? Causes the user to be electrocuted. Okay. Right. Usually I wouldn't use the word electrocution because electrocution is more like a capital punishment. I would say that the user to be electric shocked, right? Electric shock. Okay. Right. Yeah. I guess the key phrase is to say that when the appliance causes, when there's a surge in current, I think we should always start with a surge in current. So I basically I've answered whatever I think I said just now, right? I've answered the question with whatever I say. If there's a surge in current, the magnetic field is strong. The magnetic field is amplified in the sensing coil. The electrical device detects an increase in induced EMF. So you need to quote Faraday's law or something, because they did say Faraday's law, right? Yeah, they did, they did, yeah. So you need to talk about the induced EMF in this sensing coil, and the electrical device registers a higher induced EMF, and therefore the circuit breaker is activated. Huh? What? One more time? Will be unequal. Oh, yeah. So the idea here is that I didn't see the other wire. So the idea here is that there's another wire running up. So the current run down, the current run up. So the net field strength is supposed to be zero. Yeah, yeah, yeah. This question is way too convoluted, lah. Yeah, sorry. This one here, this is like, huh? Okay, let's put a test subject here. Okay, so let's say he is part of the circuit now. Okay, tell me how the electricity flows. Electricity will flow here into him. I'm all right, but some of it will like a little bit will go back up, right? But then that will mean that the live wire and the neutral wire, right? The amount of current is not the same. So the magnetic field from one wire and the other wire is also not the same, and then therefore the magnetic field doesn't cancel out, it's uneven now. Then the sensing coil senses the magnetic field. So what's the normal case? Sorry, let's talk about, like, let's what happens in the normal case, like, there's no, that let's say in a normal situation. I didn't read the question until, sorry. So in a normal situation, the current flows inside here, goes to the appliance and flows out, right? So one is flowing down and one is flowing up. So one of them, the current flows down, the magnetic field is this way. The other one, the current is flowing up, the magnetic field is this way. So this way and this way, the magnetic fields will cancel each other out. So the sensing coil at normal basis should not sense any magnetic fields at all. But if you have that case whereby the person is being electrocuted, like like this, right? Okay, then the magnetic field, sorry, then the current flows into this guy, and a little bit will flow back. Then you will have an unbalance. You have an imbalance of current on both wires, and therefore an imbalance of magnetic field lines. Then the sensing coil will sense it. Yeah, right. Spider senses tingling. Yeah. I sense a disturbance in the force. No, sorry, I have to keep myself entertained. I'm so annoyed by this thing. It suggests one way of increasing the sensitivity of this coil. More coils. More coils. Can already. Okay, next one. Say what? Oh my god. State and explain whether the potential at A is higher than that at B, is it? Yeesh! This is like the one thing that said that shouldn't happen. So what you're doing here is you're reducing the area. You're reducing the area of the coil. You're making the area smaller, right? Because you're pulled, right? Okay, and then there's no more loop. So there will be an induced current inside this loop. Okay, so how does the induced current flow inside the loop? So the loop of wire looks like this. So I mean, I draw it on the side. The loop of wire looks like this, right? Yeah, something like that. And then you pull it like this, right? So what's happening to the area? The area is experiencing what? Okay, let's go from scratch. The area experiences a change in flux, right? How is the flux changing? It's getting less, right? It's getting less. Right now, it's getting less, right? So it's experiencing less, right? So area smaller, right? Less crosses. Okay? Okay? So it's experiencing less crosses. So what would the area try to do? It will try to create more crosses because it's trying to oppose the action. So it will induce more axes. Okay? So if you try to induce more X, okay, rank grip rule, right? That means your induced current in the coil will turn this way, right? The induced current will go this way, right? This will be the induced current, yeah, induced current, and therefore current will flow from A to B. Out. Something like that. Okay? Then you pull it like this. Okay? Like this. Then you pull it like this until it becomes there's no more loop like this. Yeah. So you're pulling it like that. Yeah. Okay? But I think the key thing is this. What's the change and how do you oppose the change? What happens is a lot of students think that you're supposed to oppose the direction. Bro, if you push the two wires, then the circle will get bigger, right? Like this, right? Right? You understand? Yeah. So you're like trying to lasso it or something like that, like, I mean, so making it smaller. Oh man, what's going on? Okay, I'll drink more water. I haven't touched my water the whole day. Yeah, yeah, yeah. So I don't feel well, then I drink more coffee. Yeah, what's up? Yeah, you see, their coffee also one big one. What kind of coffee you drinking? So what do you order? And okay, anyway, yeah. I cannot. What? The previous one? 哪一个 previous one? Ah, why? Wait, hang on. Wait, I'm not done yet though. This is not induced current, right? But what's the question asking for? They're asking you which side is positive, which side is higher or lower potential, no? Which side is the plus side and which side is the minus side? Whether A is the plus side or A is the negative side. So what's your answer? What's your answer, guys? Huh? Why lower? You're not wrong, but why lower? Correct. So guys, whenever you're doing this kind of question, right, always imagine an external circuit. You go and connect an external circuit to a bulb here like this. Okay? How does the current flow through the bulb? Like this, right? Correct or not? When you induce a current here like already, then the current will flow through the bulb like this, right? Okay, then you go and draw one circuit like this on the side here like that. Okay, then I ask you, okay, how should you put the battery so that the current flows the same way through the bulb? Huh? Positive on this on the right side, negative on this side, right? Which means B is the positive side. Then A is the negative side. So A is the lower potential side. What's another? Okay, so I tell you this, okay. So because those who are having tests on EMI, right, this thing is gonna come out. I tell you. All right. So you kind of like understand this, current, right, for a battery, outside the battery flows from plus to minus. Inside the battery, the current flows from minus to plus. Yeah. Okay. So the induced EMF means that this loop is like an induced battery there. So current is flowing from the negative to positive side. Can okay? Can no, I'm not okay. Yeah, I'm not okay. I'm okay. Okay. What's next? Hey, what's your Monday like? You tell me. No school. Oh shoots! Monday youth day. I need to reshuffle some of these buggers. Yeeks! Sorry. I need to just send this out. Okay. Are you coming down to study next Monday? 10, 1 p.m. Hey, smack her. 1 p.m. next Monday. Zoom. Next question. The two of them waiting outside already. What's that? 6B part 3 and 4. 6 is this. Photoelectric effect. Huh? 6. Okay. So photoelectric effect. Silver, ammeter, voltmeter. Trying to be damn extra, but there's a potential meter. Why, yeah? Why? Why you do that? What's that for? I mean, the voltmeter has to reach zero, right? Oh, part 4. Oh, this is. Oh, no, this is X-ray production. It's X-ray. X-ray. Hey, why is there? Why they draw it the other way around? So annoying. They go and put a frequency graph. It's supposed to be a wavelength graph. Why? Why they do that? I don't get it. Why? I don't get it. Like it should be like this, right? This will be wavelength and intensity, right? Why they draw the wheel the other side? Then why you want to ask? Uh, it says sketch the to show. Uh-huh. So it means that the incoming electrons now has half the Ke that it had before. Your incoming electrons, right? So if you reduce the acceleration PD by half, now it's like half V. Then my Ke last time was, let's say, okay, I'll give you an example. Okay, last time it was 1000 EV. Now it is 500 EV. Okay, so what will happen to the minimum wavelength? What will happen to the minimum wavelength? It'll be a larger wavelength lah, right? So what will happen to the maximum frequency? It'll be less, but how much? Is it half? Is it directly half? Why would it be directly half? Because the energy of the electron equals to hf, right? Like let's say we assume Bremsstrahlung, right? Bremsstrahlung is all of the Ke converted into one single X-ray photon, hf. If you half the Ke, then my frequency half. So instead of the maximum frequency of 8, you will get 4. But 4, but 4 means that you can't even see your characteristic wavelength. So your graph will just look like this. A wheellet. Yes, a small wheel. A wheellet, no spout. You can't even get the characteristic to come out. So it will be just like that. And everything else, the intensity is less. You like Narwhal and Jelly? Have you read this comics called Narwhal and Jelly? Oh, okay. That's a bit weird. Which one? 6C part 2, is it? This one here? Energy levels. And then explain the minimum value of V used to give rise to the transition in part 1. So I need, okay, what sort of excitation is this? Are you using light to excite the electron? Am I using light to excite the electron? What? I'm using electricity, right? I'm using electrons. So this is electron bombardment, right? So this is electron incoming, bombard the atom, right? The electron and cause the electron to excite, correct? Okay, what was the transition for part 1 again? 4 to 2. But that's not excitation. 4 to 2 is de-excitation. Huh? Okay, 4 to 2. So they're saying that if you want the 4 to 2, then how much energy does the incoming electron, how much voltage must the incoming electron be excited to in order for 4 to 2 to happen? Which means that you need to excite it to level 4. You need to go from 1 to 4. Then you can drop from 4 to 2. You will get a whole lot of others lah. But yeah, all of them happens at the same time. So it's you have to find 13.6 minus 0.54. Next question. Almost done with section B already. Zheshen, Amanda, hang on. 8A part 3. 8. A part 3. You're supposed to show the period of oscillation. Did you sub in H already? Yeah, it is upthrust. So H is the equilibrium height, isn't it? H is the equilibrium height. Yeah, I know, right? What the heck? Okay, all right. So this one here, Anthea, look at this, I'm gonna show you magic, Omega square is rho AG over M plus M. You're supposed to find the period. 2 pi over T squared equals to rho AG over M plus M. What is the one thing that you do not have? You don't have the A? Did they not give? So you see, right, we are one step away from finding the period already. We're one step away. So do you have M plus M? Don't have. Do you have A? Don't have. Do you have density? You macam everything also don't have. Then what you do? Then we have no choice. So what's big M or what's small M? So small m is the test tube, big M is the ball bearings. So this is what? M plus M G, right? Then the up thrust is what? Up thrust is rho Vg, right? And rho Vg will be the density of water, right? And V, what will be V? A times H, right? And G. So rho water AHG equals to M plus M bracket G. Can I do some magic with this? Am I able to do some magic with this thing here? I think can. I think I can get rid of some things there. Right? Let me just. Oh, I can't paste it over here. What? Yeah, I know. It's a PDF. What did I write again? Rho of the liquid AHG equals to M plus mg, right? Can I cancel someone out? No, I can cancel G, right? I can also I can go golly over M plus M, right? I know. Rho AHG equals to M plus mg. All right. Stop. Rho liquid A divided by M plus M equals to 1 over H. This term is, what the fuck was H doing that? What's G doing there? Is this term here, rho A M plus M. So that means that this is equals to G over H. Yeah, 9.81 divided by 0.062. Fucking annoying question. Ah, what do you mean? How do I get? I'm supposed to know that from 2 chapters. SHM and circular motion. Omega is 2 pi over T. Period. Some more. This capital T is. Oh. Oh, okay. No. Okay. So this particular question, the moment I saw it, I know that this is a classic SHM question. And since it's a classic SHM question, we know that SHM means A equals to negative omega square x. So what I did, I just compared coefficients. Okay. I thought you meant why the omega is the T. I want to whack you really. What? V double I, is it? V double. Huh? Wouldn't the graph just look like that? Is what? two? Why got two one? Huh? Yeah, shouldn't it be one? Yeah, so? Oh. So so this is the this is the free oscillation of the tube, right? You push it down one time, then it will oscillate, correct? So what's the natural frequency of this tube? And I'm asking you, what's the natural frequency of this tube? So the natural frequency, natural F, is equals to 1 over period, which is 2 hertz. Is it not constant? It is constant. So this is the natural frequency. This is the natural period of that tube. This is the natural frequency of that tube. So when the driving frequency matches the natural frequency, what you get? You get resonance, which is why in this graph, when you draw it like that, the natural frequency here is 2 hertz. Is that what I thought you meant the amplitude is 2 hertz, huh? No. Okay, can next one. Last one. I see you guys on Monday, okay, on Zoom. Yeah. Use more ball bearings. From that part that we did just now, 2 pi over t squared equals to g over h, right? G over h, right? Wait. Something wrong. I made a mistake. When water waves of 0.3 hertz are generated on the surface of water, the amplitude is rather small. So basically, Anthea, what they're saying is that their driving frequency is only 0.3 hertz. The driving frequency can't reach 2 hertz. So if you want resonance, right? You want to increase the amplitude, right? If you want resonance, what can you do to your test tube? Basically, you adjust it so that the natural frequency is closer to 0.3 hertz. Right now, the natural frequency is 2 hertz, right? So you have to adjust this natural frequency to, right? Adjust the natural frequency of the tube to 0.3 hertz. But how do you do that? How do you reduce its natural frequency? So yeah, sorry, it's from the previous it's on here. Okay, so it's basic. Sorry, it's 2 pi f squared equals to g over h. So if you want to decrease the natural frequency of the system, you increase the h. That means, yeah, you increase the h. You want smaller f, right? You want a smaller f going from 2 hertz to 0.3 hertz. You use a smaller f, you get a smaller f. In order to get a smaller f, you must have a bigger h. Bigger h means that the tube is sunk in more, right? Because h is the amount of height of the tube that's been sunk in, right? That's h, right? So if you want it to sink in more, you have to use more ball bearings. You add more ball bearings to the system. Yes, yes. That's right. Yeah. No, don't worry lah. Yeah, you it's okay one. Don't worry. Yeah. Okay. Can I see you guys on Monday lah. Then I settle all your questions. Somehow it's only you right now. Then you got questions on you. Will you have on Monday? You will have on Monday. Okay, bye. This Sunday is gonna be nuclear. I'm gonna see you, right? Okay, this Sunday is nuclear. I'm gonna see her and Roshni. As in, I'm starting this Sunday, but I don't think I'll do tandem because I think I don't know. I think maybe you all need a break. So for those who are coming next Thursday, that will be the first lesson of nuclear also. Not for now lah. You not shag meh? Shag lah, right? Shag. Okay, so go back to one lesson a week first, right? But don't worry, like if I need a tandem, I will just call for tandem and you all just get more time to do more practice only. That's all. Okay, can. Huh? Yummy, pass it to the ones outside. Okay. Afni, thanks very much. Thank you, bye.